Now let's investigate the demagnetization refrigerator. The magnetic property of an atom or nucleus is used in the demagnetization cooling process. Below a certain temperature, just the magnetic order determines the temperature. All of the other elements have frozen and are no longer contributing to the overall temperature. Most materials' lattice motion comes to a halt at around 1 Kelvin. Furthermore, at this temperature range, metal conduction electrons are also frozen. As a result, if a material contains magnetic ions, the order of these magnetic ions controls the temperature of the material. Even these magnetic ions are spontaneously ordered below roughly 1 millikelvin, since the magnetic interaction between the magnetic ions is significantly larger than the thermal energy in this low temperature range. Even at this temperature, the nuclear magnetic spins do not align. The temperature is thus determined by the ordering of these nuclear magnetic spins. The temperature is decreased during demagnetization cooling by controlling the magnetic ordering. Atomic magnetic characteristics are used in electron demagnetization cooling. Nuclear magnetic characteristics, on the other hand, are used in nuclear demagnetization cooling. Isothermal magnetization and adiabatic demagnetization are the two processes that make up demagnetization cooling. An external magnetic field aligns the atomic or nuclear dipoles in the first process, isothermal magnetization process. The precooler observes heat generated in this process, and the process is done isothermally. The magnetic field is removed in the second process, adiabatic demagnetization. We must first thermally isolate the refrigerant from its surroundings before turning off the external magnetic field in the adiabatic demagnetization process. As a result, the demagnetization is done adiabatically in this process. Without an external field, the magnetic dipoles are randomly oriented as seen in the figure below. Equal 0, magnetic dipoles are oriented randomly. When an external magnetic field is applied, however, they align with the external magnetic field as well. So if we apply external magnetic field, the dipoles are aligned. So this process is the isothermal magnetization, and during the magnetization, the heat is generated, and this heat is absorbed by a precooler such that this process is performed isothermally. And adiabatic demagnetization process, we first isolate the refrigerant, using heat switch. We will discuss this heat switch later. And then we removed the external magnetic field. That is the adiabatic demagnetization process. Okay, then the temperature will be reduced. Let's explore what happens if we eliminate external magnetization in the adiabatic demagnetization process. Due to the external magnetic field, the magnetic dipoles are forced to align. Yeah. As a result, once the field has been removed, they will attempt to return to their previous randomly oriented state. So this state. However, they are unable to do so. They require thermal energy to change their orders. However, the process of demagnetization is carried out adiabatically. As a result, the magnetic dipoles are unable to change their orientation. Only the order of the magnetic dipoles determine the temperature in this temperature range. A lower temperature is related with the ordered state. As a result, magnetic dipoles must spend their internal energy to remain their order, reducing their own temperature. The essential principle of demagnetization cooling is outlined above. Demagnetization cooling is composed of two processes: isothermal magnetization and adiabatic demagnetization. The heat generated during the isothermal process is absorbed by the pre-cooler, which makes the process isothermal. Let's see the superconductor heat switch. This is essential for the demagnetization cooling, because we have to connect the refrigerant to pre-cooler, and also we have to shut off the refrigerant from the pre-cooler. So that kind of function can be done by the superconductor heat switch. The demagnetization cooling process requires the superconducting heat switch. It makes use of superconducting wire heat switch. So this is superconducting wire. Between the pre-cooler and the refrigerant material is a superconducting wire. For the electronic and nuclear demagnetization cooling, the helium 4-part evaporator and dilution refrigerator are used as pre-coolers respectively. Commonly used superconductor wires include those made of lead, indium, aluminum, and other alloys. The electrons form co-pairs and do not conduct heat in the superconducting state. As a result, only the lattice can transport heat in this state, in this superconducting state. The lattice's ability to conduct heat is related to the temperature Q, Tq, at these low temperatures. Heat conductivity in heat conduction by the lattice is negligible because the cube of low temperature is so small. So in the superconducting state, the superconductor wire cannot conduct heat from pre-cooler to the refrigerant material. Due to the inability of heat to conduct from refrigerant to the pre-cooler in the superconducting state, the switch is turned off. Now, applying a magnetic field above the superconducting wire's critical field will return them to their normal state. Since the heat conduction of the electrons is proportional to the temperature, conduction electrons carry out heat conduction in the normal state. So in normal state, the superconductor material become normal state, and heat conduction can be possible. As a result, the heat switch represents the wire's superconducting state, and the switch on indicates the wire's normal state. So, the superconducting state corresponds to switch off, and the normal state corresponds to switch on. Okay. In the mid-Kelvin temperature range, the ratio of heat conduction in the normal state proportional to temperature T to that in the superconducting state T cube is larger than 10 to the 6. So we may therefore employ superconducting wires as heat switch due to this high heat conduction ratio. Okay. The heat generated by the magnetization process should conduct to the precooler for the isothermal magnetization process. This can be done by applying a magnetic field to the wires that is larger than critical field. So for example, 10 millitesla for aluminum wires in order to bring the wires to their normal state. So switch on, then turning on the switch, heat switch. On the other hand, the refrigerant needs to be thermally isolated from the surrounding throughout the adiabatic demagnetization process. So in this case, the switch needs to be turned off, which may be accomplished by removing magnetic field. A few Kelvin is wire's superconducting transition temperature, so precooler or refrigerant temperatures are lower than this transition temperature. So as a result, the precooler and the refrigerant connected wires transform into superconductors. So we can use a small magnetic field to switch on and off of the superconducting wire. So if we apply a magnetic field rather than critical field, then superconductor will become a normal fluid. So that means normal state. So in that case, switch on state. So heat can be conducted from the refrigerant to the precooler. In the isothermal magnetization process. On the other hand, in the adiabatic demagnetization cooling process, switch should be off because no heat should be input to the refrigerant. So in that case, we removed magnetic field. Then the temperature of the surrounding is less than the superconducting transition temperature, so the wire become superconductor, and the heat cannot be transferred from the outside to the refrigerant. So the process can be done adiabatically. Okay. So in this superconducting state, the wires are unable to convey heat, making the adiabatic demagnetization process possible. Now let's see the enthalpy. Let us now look into or demarcation cooling from an entropy viewpoint. The measure of a system's disorder is entropy. The entropy of a disordered system is higher. The ordered system, on the other hand, has lower entropy. The entropy of the liquid state is generally lower than that of the gas state, and the entropy of the solid state is the lowest. At room temperature, water, for example, is liquid. When the temperature drops below 0 degrees in centigrade, however, water transforms into ice, which is its solid state. When the temperature increases above 100 degrees centigrade, however, the water transforms into vapor, or gas state. The most disordered state is water vapor, which has the largest entropy. On the other hand, it is ordered and has the lowest entropy in the ice state, solid state. The entropy of a system decreases as the temperature is reduced. As a result, lowering the temperature is the process of decreasing entropy. The entropy is affected by a number of parameters, including temperature, pressure, volume, magnetic field, and so on. If we want to lower the temperature of a system, we change one of these parameters. A cooling parameter is what is termed. The magnetic field is used as a cooling parameter in demarcation cooling. We can align magnetic dipoles and so reduce the entropy of a system by applying a magnetic field. However, this process should be carried out at a temperature where other parameters have no effect on the entropy, and the temperature of the system is determined only by the alignment of the dipoles. This temperature is around 1 Kelvin for electronic demarcation cooling. The lattice motion comes to a halt below 1 Kelvin. As a result, the temperature is solely determined by the magnetic dipole orientation. On the other side, we must begin the cooling process for nuclear demarcation at around 1 millikelvin. All motions except the nuclear magnetic dipole orientations stop below 1 millikelvin. Hence, the temperature is solely determined by the nuclear dipole order. Consider the case of a system of free magnetic dipoles. This system can actually be thought to be electronic or nuclear magnetic dipoles. The dipole's magnetic moment is given by this relationship, when its total angular momentum is J. So J is total angular momentum, and mu B denotes Bohr magnetism, and G denotes the Lagrange G factor, which is determined by spin and angular momentum vectors' relative orientation. This is for the electronic magnetic dipole. For the nuclear magnetic dipoles, this should be nuclear magneton, UN. The energy levels of magnetic dipoles are split into 2J plus 1 possible states if they are placed in the magnetic field B. The magnetic quantum numbers corresponding to these states represented by M, which are minus A to J, 2J plus 1 possible states. The energy of each level is then written as this equation. So the energy of a magnetic dipole in the field is given by minus mu dot B. So we have this equation. It's magnetic quantum numbers M. So we have 2J plus 1 different energy states. As a result, magnetic dipoles can exist at energy levels separate uniformly by G mu BB. The partition function obtained if n magnetic dipoles are replaced in magnetic field B is this equation. So there is a partition function of n magnetic dipoles, free magnetic dipoles. Here x is represented by this quantity. The entropy of a system is determined using this partition function by this relationship. So we have entropy of free magnetic dipoles in the magnetic field given by this equation. So x is the function of p over t. Others are constants. So the entropy of this system is only a function of one variable, p over t, as shown in the above equation. So function of x only. Okay. The magnetic field of Bi magnetizes the magnetic dipoles at temperature of Ti, so initial temperature and initial magnetic field. This is a process of isothermal magnetization. The magnetic field is then adiabatically reduced to Bf. We can turn off the magnetic field. Let's say we reduce the magnetic field down to Bf. The entropy of the system should not be changed because this process is carried out adiabatically. Okay. The system's initial entropy is a function of Pi over Ti. The system's final entropy, on the other hand, is just a function of Pf over Tf. So entropy should be unchanged during this process. So we have this relationship. So before demagnetization process, after demagnetization process, entropy should be the same. So this relation holds because the entropy should not change after the demagnetization process. As a result, the minimum temperature that demagnetization process can achieve is given by this equation. According to the relation above this equation, absolute zero can be obtained if the final field becomes zero. So we turn off magnetic field completely, then Pf becomes zero. So we can have absolute zero temperature. However, that's not possible because dipole-dipole interactions produce an internal energy, internal field. So internal field is still there even if we shut off the external magnetic field, the still internal field is there. So the absolute zero cannot be achieved. The total magnetic field experienced by magnetic dipoles is the vector sum of the applied and the internal fields. Okay. This vector sum's magnitude is determined by this local field is given by this equation. P is external field and P in is internal field. So we can have this local field. So magnetic dipoles experience this internal field. As a result, the final temperature we can achieve is modified to this equation. So even if we shut off the external field, we cannot get the absolute zero, but at a certain temperature close to the absolute zero. The lowest temperature is reached when the applied field is entirely eliminated during the demagnetization process. So the lowest temperature is given by this equation. So this is the original equation, and the internal field P in is generated by dipole-dipole interactions. We omitted here in this process out of the denominator here, because this value is very small compared to Vi, so we can eliminate this term. So we have this equation. So we omitted P in out of the denominator since it is so small in comparison to Vi. The product of magnetic dipole moments determines the magnetic magnitude of dipole-dipole interactions. Dipole-dipole interactions can be written by this equation. The potential between two dipoles, mu1 and mu2, is given by this equation. So the product of these two magnetic dipole moments determine the dipole-dipole interactions. Okay? The magnetic dipole moment of the nucleus is 1/2000 times smaller than the magnetic dipole moment of the electron. As a result, in nuclear magnetization cooling, we can achieve a significantly lower temperature than in electronic demagnetization cooling. Paramagnetic salt is used as a refrigerant for electronic demagnetization cooling. A small number of magnetic ions can be present in paramagnetic salt in this salt system. These ions from magnetic dipoles inside the salt. Refrigerants including salts such as CMN, CPA, FAA, and MAS are commonly utilized for the refrigerant in the electronic demagnetization cooling. In this CMN, CPA, FA, MAS, C, chrome, iron, mangan ions are present in this paramagnetic salts. The lowest limit of this electronic demagnetization cooling is about millikelvin, so which is obtained from the dilution refrigerator. So this electronic demagnetization cooling method actually is not used for cooling. Instead, this paramagnetic salt is used for measuring the temperature. In the entropy versus temperature diagram here in this figure, the figure below depicts how the demarcation process is performed. At temperature of Ti, so here, starting from A, the isothermal process starts. Okay. The magnitude of magnetic field for magnetization determines the entropy reduction. So if we use small magnetic field V1, this entropy reduction is very small. But if we use large magnetic field or magnetization field, then entropy reduction is larger. Okay. So the magnitude of the magnetic field for magnetization determines the entropy reduction. As illustrated in the figure, a stronger field indicated by X, results in a larger entropy reduction, and as a result, the greater cooling power. The final temperature in the demarcation process is also dependent on the final field. You see in this diagram. We can get the lower temperature by using a smaller final field. So if we use a smaller magnetic field P equals 0, for example, we have a low final temperature. If we use final temperature V1, then we have a little higher temperature. And the cooling power for this process A to X to X to C here, the cooling power is given by this blue area. Okay, so this demarcation process finished here, then temperature increase following this line. Okay. On the other hand, if we use the final demarcation field of P1, the final temperature is here, and from here the temperature will increase following this line. So we have more cooling power. This area, this represents cooling power. So if you use the lower demarcation field, then we can have the lower final temperature, but cooling power is less. However, if we use the little higher demarcation final magnetic field, then you can have a slightly higher temperature, but cooling power will be larger. Okay. At temperature Ti, isothermal magnetization takes place starting from here. If a stronger magnetic field is employed for magnetization, the entropy reduction increases. So here A to X process has great entropy reduction than A to X prime process. Okay. If we employ a lower final magnetic field for demagnetization process, we can get a lower final temperature, Tf P equals 0, is lower than T prime F here. Okay. We can obtain more cooling power if we use a larger magnetic field for the demarcation process. So if we use a larger demarcation field, then temperature is higher, but we can have more cooling power.